In this section, we're going to look at inverse functions. Inverse functions are important for when we get to the exponential and the logarithmic function. That's a famous pair of inverse function. The log function is the inverse of the exponential. And then later on in your studies, the inverse trig functions. Okay, so first let's just study inverse functions kind of as a standalone. And we'll start with an example. Here's an example of two inverse functions. Fahrenheit to Celsius and Celsius to Fahrenheit. If I have an input of Celsius, the output would be Fahrenheit. And this other function, which I'm saying is the inverse function, if I have an input of Fahrenheit, the output is Celsius. Let's take a look at what it means to be inverse functions. One way to describe them is that one function undoes the other. So let's say I plug in a certain temperature in Celsius into this function, input C, output F. I get that output and run it through the other one. What will happen? Well, I should be right back where I started. For example, let's take 122 degrees Fahrenheit. That's pretty warm. 122 degrees Fahrenheit. If I plug that into my C, right here, then I get an output of 50 degrees Celsius. Okay, so I perform the operations, and these are linear functions. I perform the operation, and that is I subtract 32. 122 minus 32 is 90. 5 nines times 90 is 50. So 122 degrees Fahrenheit is 50 degrees Celsius. Now I take that, and I just plug it into my other function, my Fahrenheit function. What happens? Well, I plug it into this function, my other function. I take the Celsius value of 50, 9/5 of 50, that should be 90, and then plus the 32, and I get 122. So I'm right back where I started. So one function undoes the other one. That's one way to look at it. Here's another way to look at it. So the input for the Celsius was 122, so that's input, which a lot of times we use X, 122. And the output, a lot of times we use Y, would be 50. And look at this other function. If I input the 50 and put 50 here, what happened? I got an output of 122. And this is a trend that's going to hold up. That is, your X values here will be your Y values here, or your inputs here are your outputs in the inverse function. And your outputs in your regular function will be your inputs in your inverse function, as we're going to flip the domain and range. So we'll talk about that property, very important property, and some other properties of these pairs of functions. Okay, but first a note, here's the notation we'll start using. This is my regular function notation, and then my inverse function notation will look like that. Okay, just a quick note, this means this little -1 exponent sometimes means reciprocal. Like if you remember exponents, 2 to the -1 was 1 over 2 to the 1. That's not how we're using it here. It has a couple meanings, I guess. This is the reciprocal version of the little -1 exponent, and what we'll use it for is the inverse function. Okay? All right, let's take a look. So if you believe me that the function undoes the other, that means if I compose a function, so here's one property of inverse functions. If I compose a function with its inverse, I'll be right back where I started. All right, and then if I compose an inverse with a function, I'll be right back where I started. That's one way to define that. So let me give you a quick example to make sense of this first definition. This is the first big time property of inverse functions. So let's do an easy one. What do you think undoes cubing a function? Well, how about the inverse would be the cube root? Okay, so if I apply this to a number, if I cube a number, let's say f of 2, that's 2 cubed, that's 8. And if I plug that into the inverse function, of course, what's going to happen is I'm going to cube root 8, and I'll be right back where I started at 2. But we can do this, what this means is we can do this for all values of x. So, and I'll end up with that 2, or with just the input. So for example, if I wanted to say, okay, let's try and prove that these two functions are inverses. It makes sense that they're inverses, But let's try and establish that using this rule here. They're using G, or I'm using G for F inverse, but I could also use this notation F inverse. So F of F inverse, or G, of x means I plug in into my function f, x cubed, the other function, cube root of x. Okay, so there's some simple algebra to do here. The cube root of x cubed is x. That's what this definition means. That's instead of doing it for one particular value like 2, I can do it for all particular values and call it x. All right? So we're going to do a couple more of those coming up. That's one property of inverse functions. If you compose a function with its inverse, you get your input x. What else is true? Well, we talked a little bit about that. The range of f is the domain of g. So let's g, when I say g, I could also use f inverse, either one. So if I take that cube function, that is f x, f of x, and just pick a couple values and cube them. -1, 0, 1, 2. Cube it. -1, cube it. 0, cube it. 1, cube it. 2 cubed is 8. What does an f inverse look like? Well, for that example, my cubed example, what would my inputs be? Well, I want inputs to this function that I could take the cube root of to make it easy, right? So maybe, well, I can take the cube root of -1. I can take the cube root of 0. I can take the cube root of 1. I can't take the cube root of 2, but I can take the cube root of 8. I can take the cube root of 27. Cube root of -1 is -1. Cube root of 0 is 0. Cube root of 1 is 1. Cube root of 8 is 2. Cube root of 27 is 3. And look what we got here. We have the outputs of my function f are the inputs of my function f inverse, right? These match up. And that's what this first property is saying. The range of f is the domain of f inverse, or g. Okay, another important property for our inverse functions. So let's see what else we got. We can talk about the graph as well. So let's take a look at what this means for the graph. Okay, so if you have some kind of function here, let's say the point 1, -1. I'm sorry, -1, 1 is on the function. Then what has to be on the inverse function? Well, you flip the x and y, right? So if I flip the x and y, then -1, or I'm sorry, y becomes x, 1 comma -1, so I just kind of flip these guys around just like we did over here, ends up on the graph of the inverse function. Okay, so you're literally flipping x and y, so this becomes a reflection around this line, y equals x. Any function I graph, if I can reflect it around the line y equals x, I'll get the graph of the inverse. So that is, how would I reflect it? Well, you can just flip these two numbers like I did, or the other way is you travel the same amount from here to here as you would from here to here, and you'd be on your inverse graph. Okay? I know I'm throwing a lot of properties at you here, but let's take a look at some examples. Okay, let's do the verification, and we're going to do this by composite, by composition of functions. Okay, by composition of functions. So that means I got to take this function and plug it into here. All right, so c equals 5/9 input 9/5 c plus 32 minus 32. All right, so let's slow down for a second here. What did we just do? We just took this input variable, which is called f, and we plugged in our entire function here because that's what f is equal to. Okay, and what should happen? Well, we should have that undoing process, right? That is, when I do this, I should end up with just my output of the variable that we started with. Okay, so let's see what happens. F, you plug in f here. See what happens. Equals 32 minus 32 is 0. And then you get C equals 5/9 times 9/5 C. And you end up with just the input variable. Okay. That one's a little confusing because I'm using, I think that is a little confusing because I got C equals C, which is a true statement. But let's say here's how we're going to see these in the future. So I would usually say f of x equals 9/5 x. See if this clears anything up, plus 32. And my inverse function is 5/9 x minus 32. Okay, instead of using these C's and F, we would typically use our function notation. And then I would say, okay, let's say what we want to do f of f inverse, and we also have to do f inverse of f. That is, we have to do both compositions. So if I take f of x, if I'm calling this f of x, and plug it into f inverse, just looking at these guys now, then I would say 5/9 times x. I'm going to plug in the whole f of x into the input, which is 9/5 x plus 32 minus 32. That's that's the composed function. That is, this is where x used to be, x minus 32. But what did I do? I took out x and I plugged in the entire function. Okay, and what happens when I do that? Well, the same thing. 32 minus 32 is 0, and then I get 5/9 times 9/5 x, which is just x. If we did it the other way, then you got to take this function and plug it into that x, right? So 9/5 x plus 32. This is how I write these sometimes. 9/5 x plus 32, and I just draw a blank for where x was, and I plug in the entire function, which is 5/9 x minus 32, running out of space. So the order of operations is different. I got to multiply first, so 9/9 is 1, 5/5 is 1, and that leaves me with just x minus 32 plus 32, and then those go away, and I end up with x for both cases. Okay, one more. Remember, g and f inverse are the same thing here. So I can say f of g of x, or f of f inverse, is take that and plug it into here. This one's a little bit easier. 4x, instead of 4x, it's 4 times the other function, 1 over 4x. And I'm trying to decide if these are inverses of each other, but look, this one actually doesn't work out. So you'll see some of these. Verify if each of the functions are inverses of each other. So the 4's cancel out, I get 1 over x, and I can say not inverses. I don't even have to do the other one because they both have to be equal to x.